This video is going to deal predominantly with calculating z-scores and using them to get percentile answers for questions. But just before we get going, just wanted to harp a little bit more on shifting and scaling. If you just take a minute and pause and just sort of copy down the yellow parts in this page, I think it would be very helpful. Shifting, again, is by adding or subtracting in parentheses a constant to each value, and all measures of position will increase or decrease by that constant. But adding and subtracting a constant leaves measures of spread unchanged. Whereas when we multiply or scale, right, remember, when we're talking about multiplying, we're talking about scaling, all measures, right, and even the measures of spread change. And then over here in this picture sort of just highlights what's going on. In the first picture, we have the distribution of weight in kilograms, and in the second picture, we have the distribution of weight in pounds. And what's different about these pictures? Not much. They both have the same amount of outliers, same sort of skewness. It's just one's a little teenier than the other, because when you go from kilograms to pounds, you scale. One of the big reasons you know that we've scaled is when we look right here, our measures of spread, IQR and standard deviation, have changed. When we go from the kilogram, 25, to the pound side, 55 for the IQR, and for standard deviation, 22.27 to 48.99. That's a clear indication that we have multiplied because measures of spread changed. Again, I highly suggest you copy the yellow highlighted sections and reread them after you copy them. Just a few more notes before we move on into the calculations. We sort of take that shifting and scaling conversation, and right in here, this first sentence is really huge. Standardizing data into z-scores is just shifting them by the mean, that's the subtraction of the mu, and then rescaling them by the standard deviation, that's the division part. So that whole z equals x minus mu, that's the shifting part, and then the dividing by standard deviation, that's the scaling. Down at the bottom it says, well then how does standardization affect the distribution of the variable? Right here. It does not change the shape, it just changes the center by making it to 0, and it changes the spread by making the standard deviation worth 1. Why do we do that? Because our standardized normal model is something that we know a tremendous amount about in terms of percentiles. So if we can change the conversation from raw scores into a standardized score, we can talk about things in a very intelligent manner. So as we look at our first question, we're talking about IQs. As you see here, IQ is normally distributed with a mean of 100 units, quality points, and a standard deviation of 16 quality points. And the first question asks me, what percent of people's IQs would you expect to be over 80? So as you see over here, I have my normal model drawn, and my mean right in the middle. It's kind of a haphazard normal model, but a mean of 100, I always put the mean in. And here's 80 to the left, and it's over 80, so we're shading to the right. So now what we want to do is we want to calculate a z-score. If we're looking for what percent, we need a z-score. Remember, z-scores in, percents out. So go ahead, take a moment, calculate the z-score for 80. I get a z-score of negative 1.25, or somebody who scored an 80 on the IQ would be 1.25 standard deviations below the mean. Now, let's move on to our calculator. So what I've gone ahead and done is taken the liberty of creating a calculator screenshot. I went to second vars, right, that's second vars on my calculator, and then I go to norm CDF, right? Norm CDF on my calculator. And I get to some sort of screenshot like that. Or for TI-83s, you're going to go right to your screen, norm CDF. Now, what do I need to do? I need to tell the calculator what the lower bound z-score is and what the upper bound z-score is. The upper bound z-score for my bounded area right here is positive infinity. So I'm going from 80 all the way to positive infinity. 80 is associated with the z-score of negative 1.25, and positive infinity is associated with 10 to the 99. Either way, for the TI-84, I'm going to hit enter, paste it. Right here is the word paste. I'm going to paste that command in, hit enter until I get to this answer. Or I just hit enter for my TI-84 and I get to that answer. So it's approximately 89.43%. And that makes sense because from the mean to the right is half of our population, or 50%, plus the little extra doodad over here, which apparently is 39.43%. Let's try the under 90 question next. For the what percent would be under 90, why don't you take a minute, draw the picture, calculate the z-score, and then stop. Press pause now and try that. Okay, here's my drawing. Under 90, start at 90, which is below my mean of 100, and less is to the left. Less is left. So we're looking for the area that's bounded between negative 10 to the 99, or negative infinity, right? This is going to refer to negative infinity, all the way to 90. What percent is there? Well, definitely less than 50% because we're to the left of 100. What is the z-score associated with 90? That's our negative 0.625, or less than negative 1 standard deviations, or a little more than a half of a standard deviation below the mean. So now we're going to go to, again, second vars in our calculator. And what are we looking for? The left bound, or our lower bound, and our upper bound values. Negative 10 to the 99 is our lower bound, and negative 0.625 is our upper bound. Go for your calculator and see what you get. I get approximately 0.26598, or rounded to the nearest hundredth of a percent, right? At fourth decimal place, because 8 is bigger than 5, I'm going to round the 9 up to a 0, so that's approximately 26.6%, which seems reasonable with respect to our picture. Last one, between 112 and 132. See what you could do about taking this one all the way through on your own. Press pause now. All right, here it is from soup to nuts. Between 112 and 132, those are both to the right of 100, so the bounded area is shaded in. Now, the z-score associated with 112, I calculated to be 0.75. The z-score associated with 132, I calculated to be 2. Now again, going into my calculator, norm CDF, the calculator wants a lower bound and an upper bound. It doesn't care if it's infinity is involved or not. I just need an upper bound and a lower bound. Now, because there are finite boundaries on this particular problem, there's no infinity, or no 10 to the 99. So the lowest value is the z-score associated with 112, and the highest z-score is associated with 132, which gives me a decimal answer of 0.20387, rounded to approximately 20.39%. So based on the normal model describing IQ scores, I would expect around 20.39% of people to have IQ scores between 112 and 132 quality points. Exciting stuff. Okay, so going back to these exams and standardizing scores, take a minute and you read this question about 2 exams and 2 people taking the exams. Take a moment and read the question yourself. Press pause. So again, this brings into consideration raw scores versus scaled scores. And scaled scores take into consideration how the value plays into the distribution of numbers. Now, if you take a look up here, I've extracted the information about the exams and I've placed an N in front, stating that these scores are normally distributed. If they're not unimodal and symmetrical, we have no business doing this. But we're going to go ahead and proceed on the assumption that they are. So what you need to do is calculate all 4 z-scores. The z-score for Reginald and Sarah on both the first exam, and then both of their z-scores on the second exam. Go ahead and do that now. Press pause. You should have gotten the same z-scores that I've calculated. Now, Here's the interesting fact. On the first test, Reginald just scored average. He's neither above nor below the mean. He's right dead smack on the mean. Sarah, however, has a z-score of 2. She is in the pretty high, upper percentile of scoring range. She really crushed that exam. Another noteworthy piece is that the standard deviation on the first exam is 4 points, whereas the standard deviation on the second exam is 15 points. So I'm looking for you to say, wow, there was a lot of variability in scores on that second exam, whereas most people scored fairly consistently on the first exam. On the second exam, Reginald does score 1 standard deviation above the mean, and Sarah did score poorly, but she was only 0.3 repeating standard deviations below the mean, so she really wasn't that bad. So when you look at their overall performance on both tests, Reginald is 0.1 standard deviations ahead of the game. But the way I see it, Sarah overall is plus 1.7. So I would say that Sarah has a pretty good argument for why she should get a better grade. Who knows? These last few questions, then, I feel that you should try to conquer on your own. Number 3 is what we did in class. What percent of students have ACT scores less than 13? Here's the information up here about the ACT scores. So I'll draw in the pictures, and then I'm going to give you the answers. Come to class with questions about how I got these answers. So for number 3, as we've got in class, 3.12%. And number 4, what percent of students have ACT scores greater than 26? It's 13.77%. For each of these questions, you should calculate one z-score, and then using your calculator, the first one's going to be negative infinity bound by upper score of the z-score associated with 13. And for number 4, you're going to need the z-score for 26, and the upper bound is going to be positive infinity. Again, I already have these answers in for you, but for number 5 and 6, 5 is 25 and 30, so that's that finite bound. So you're going to want to go into your calculator, and you're going to put a lower z-score associated with 25, and the upper z-score associated with 30. For number 6, this is the sort of the opposite of what question 4 asks. Instead of over 26, they ask for under 26. Well, keep in mind that those two questions together should add up to be 100%, or 1 in a decimal form. So you could just subtract your answer from 4, the answer for number 4 from 1, and you get 0.8623. But if you actually go into your calculator and go norm CDF for negative 10 to the 99, comma the z-score that's associated with 26, and enter. I know that's kind of a haphazard notation. You can't put that in your calculator like that. You'll get 86.23% as well. Hopefully, this was all very helpful. And hopefully, you can calculate these answers on your own. If you can't, make these your first question next class.